180,000 pounds of steel is rounding a curve at 168 miles per hour. No steering wheel, no one turning anything. And the train doesn't even think about leaving the track. That should bother you more than it does. Because if you drop a marble onto a flat table and nudge it sideways, it rolls off the edge. A train wheel sitting on a rail is not that different, at least on paper. A heavy cylinder balanced on a thin strip of steel, being asked to follow a curve at speeds that would make a sports car driver sweat. The forces trying to throw it outward are enormous. And yet, it stays. Every time, with a precision that would embarrass a surgeon. What's actually keeping it there has almost nothing to do with what you'd guess. And once you see it, you will never look at a set of train tracks the same way again. Here is what most people assume. The wheel has a flange, that small raised lip on the inside edge, and the flange presses against the rail and stops the train from sliding sideways. That part is true. But here is what engineers discovered a long time ago. If the flange is doing most of the work on every single curve, you have already failed. A flange grinding against a rail on every bend at high speed would wear both the wheel and the rail down to nothing inside a few thousand miles. Relying on the flange to steer a high-speed train is like steering your car entirely by dragging one tire along the curb. Technically, it works. Practically, it destroys everything it touches. There is another problem nobody mentions. The flange does not prevent the train from tipping. It only prevents sliding. Those are two completely different threats. At high speed, tipping is the one that kills people. A train that slides fails slowly. A train that tips fails instantly. So the flange is solving half the problem and doing it badly. The real solution had to go deeper. It is built directly into the shape of the wheel itself, and it has been for over 150 years. Look at a train wheel from the front. It is not a flat cylinder. The surface that contacts the rail is slightly angled, wider at the inside, narrower at the outside. That shape is called a taper, and it is the single most important piece of geometry in all of rail transportation. That tapered shape means both wheels on a shared axle are always slightly different diameters depending on exactly where they sit on the rail. When the train drifts even slightly to the right wheel moves to a slightly wider part of its taper and starts rolling on a larger diameter. The left wheel moves to a narrower part and rolls on a smaller diameter. A larger wheel covers more ground per rotation than a smaller one, so the right side pulls ahead, and the whole axle steers itself back to center. No motor, no computer, no driver input, just geometry doing its job, silently, thousands of times per mile. The best way to feel this is to find a paper coffee cup and roll it across a flat table. Not a straight-sided cup, a tapered one. Wide at the top, narrow at the bottom. Roll it and watch. It does not go straight. It curves. The wider end always pulls ahead. The cup traces a perfect arc without you steering it at all. That is exactly what a train wheel does on a rail at 168 miles per hour. In the rain, through a mountain pass. What makes this remarkable is that nobody calculated it from first principles in a laboratory. The taper was not invented. It was discovered by watching what happened to wheels that were not tapered. Early rail wheels were flat cylinders, and they hunted constantly, drifting side to side in a slow rhythmic oscillation that wore rails unevenly and made passengers feel like they were riding inside a paint mixer. Engineers noticed that wheels with a slight natural wear pattern behave better, smoother, more stable, and they started building that wear pattern into new wheels from the beginning. The solution was hiding in the evidence left behind by the problem itself. Now here's where common sense breaks down entirely. If self-steering wheels are so effective, why do high-speed trains need anything else? Why not lay flat track, build tapered wheels, and let geometry handle everything? Because flat track on a curve is actively working against you. Picture driving at highway speed and hitting a curved-off ramp with no banking. The road is completely flat. Your body gets thrown toward the outside door. Your tires fight for grip. You slow down instinctively because your body knows something is wrong. That is centrifugal force. And on flat track, a high-speed train feels every pound of it pushing outward toward the outside rail. At low speeds, manageable. At 168 miles per hour through a sweeping curve, it is not uncomfortable. It is structural. It is trying to tip the train. A fully loaded high-speed passenger train weighs roughly 700,000 pounds. On a high-speed curve, centrifugal force loads the outside wheels far harder than the inside wheels. The inside wheels go light. If the imbalance grows severe enough, the inside wheels lift entirely. That is the beginning of a derailment, and it happens not because something broke, but because the physics of a flat curve at high speed make it inevitable without intervention. So engineers do something that sounds wrong the first time you hear it. They tilt the track. The outside rail of every high-speed curve is raised higher than the inside rail. Not by much, a few inches in most cases. But the effect is enormous. That tilt, called superelevation, angles the entire train slightly inward toward the center of the curve. Instead of centrifugal force pushing the train outward toward disaster, it pushes it down into the track at an angle. The weight gets redirected. Passengers stop being thrown sideways. The wheels press more evenly and firmly into both rails at the same time. Think about a bicycle racer leaning hard into a turn at full speed. The rider is not fighting the curve. The rider is flowing through it, because the lean redirects the forces into something the tires can handle. Bank track does the same thing for a train that weighs as much as 240 fully loaded tractor trailers rolling down an interstate. The amount of tilt is calculated precisely for the speeds trains are expected to travel on that specific section. Too little superelevation at high speed, and the outside wheel grinds harder into the rail with every pass. Too much superelevation at low speed, and a slow or stopped train begins sliding toward the inside rail under its own weight. Every curve on a high-speed line is a negotiation between the fastest and slowest trains that will ever use it, solved in advance and locked into the concrete holding the ties in place. That negotiation has real consequences. The same track used by a freight train at 30 miles per hour and a passenger express at 120 miles per hour cannot be perfectly banked for both simultaneously. Engineers find a compromise angle that does not destroy the freight's wheels and does not push the express toward the outside edge. That compromise is why dedicated high-speed lines, tracks built exclusively for fast passenger trains, can be banked far more aggressively than shared corridors. No freight, no compromise. No compromise means the train pushes through the same curve radius at speed shared infrastructure could never allow. But some trains refuse to accept even that limit. And what they came up with looks like a magic trick the first time you see it. The Italian Pendolino and the Japanese Series 383 do not just travel on bank track. They actively tilt their own car bodies mid-curve, leaning inward like that bicycle racer. But on command, automatically, while passengers eat lunch and coffee sits level in the cup. Sensors at the front of the train read the approaching curve. A computer calculates the exact tilt needed at the speed the train is traveling at that moment. Hydraulic systems rotate the passenger cabin several degrees inward before the curve is fully entered. Passengers feel almost nothing. A glass of water on the tray table barely moves. But outside, the train is carving through a curve that a conventional train would have to slow down for by 20 or 30 miles per hour. The tilting system is not about safety. It is about speed. The track sets a speed limit for that bend based on its fixed geometry. The tilting train exceeds it because the car body has already leaned to absorb the centrifugal force before it ever had a chance to build. The train is not obeying the curve. It is negotiating with it. Early versions of this technology had a deeply unpleasant side effect. The tilt happened fast enough to confuse the inner ear, but not fast enough to match what the eyes were seeing. Passengers watched the train lean relative to the world outside the window, while their body felt pushed in the opposite direction. Motion sickness spread through entire cars. Some early tilting trains in Europe had to restrict their lean rate just to keep passengers functional. Engineers moderated the tilt speed and capped the maximum angle. Even the solution needed its own solution. That is the complete picture. 3 layers of engineering stacked precisely on top of each other, each handling what the layer below it could not manage alone. Tapered wheels that steer through pure geometry, correcting lateral drift before it becomes visible. Bank track that redirects centrifugal force so the train presses into the curve instead of away from it, keeping every wheel loaded evenly at speed. And on the fastest trains, an active tilting system that moves the car body itself to extract speed from curves that fixed track geometry alone could never support. None of it requires a driver to steer through a curve. None of it requires a real-time computer to prevent derailment under normal operation. The shape of the wheel, the angle of the rail, and the lean of the car body handle everything before the problem has a chance to form. The system is so deeply embedded into the physical reality of the train and the track that it runs entirely below the awareness of every passenger on board. They are reading, sleeping, watching farmland blur past at speeds that would genuinely terrify them if they thought about the physics for even 30 seconds. They do not need to think about it. That is the entire point. The engineering absorbed the danger so thoroughly that the danger stopped being visible. 2 centuries of refinement made the violence of the physics underneath completely invisible to everyone riding on top of it. And that leads directly to a question most people never think to ask. If the wheels are this precisely engineered, tapered to exact tolerances, and matched to rails worn into a complementary profile over millions of miles of use, what happens when those wheels finally wear past the point where the geometry still works? You cannot pull over. You cannot jack the train up like a car on a roadside. It weighs hundreds of thousands of pounds, and the wheel is buried underneath it on a live rail line. The answer involves a machine that slides underneath the train while it sits on the track, shaves the wheel back to its correct taper without ever removing it from the axle. And the whole process happens without the train moving an inch from its position. It looks physically impossible until you understand the one mechanical principle that makes it work. If that is the kind of thing that stays with you,